dear students, my 10th graders. Today's video, first video of the series, will be related to motion. And as I promised, this will be a revision video. We will be using handwritten notes from wonderful Emily, who also allowed us to do, for me to use these notes in this video. So yeah, I'm excited to show you how you can revise better. Usually, as I say in the classes, that I'm not a YouTube video, so you should write notes. This time that's not the case, so you can just, sit back on your, maybe on your phone or on your computer or iPad. You can just go through these notes together with me. There will be some revision videos as well for past paper questions, but for now we are beginning with motion. Motion is the first topic we will be dealing with. I have also added here learning objectives. Here in the context of this first slide, we will have to describe the use of rulers or rule, and then measuring cylinders to find the length and volume. Describe how to measure time intervals using clock and digital timer stopwatches, and determine average value for small distances and short intervals. Now, there are many things that I would include, and usually I do include during the classes. However, here I will focus only on the learning objectives, and I will focus on pure things that you just need to know for the exam. However, this does not mean that some things that are not mentioned here are also not important as well. However, as I said, we are focusing only on that part. So let's start first really with SI units. SI units is an international system of units, and it is used by scientists all over the world. You will also see this in chemistry. Here we have 6 SI units, and of course we have physical quantities that are related to these SI units, which I'm going to add here as well. So meter is related to physical quantity of length. So let me just, I can write like this, length, whose length and the symbol of that physical quantity is usually L. For example, depth, thickness, and so on are also related here. Kilogram, which is related to mass, M. Second, which is time, which is T. Ampere, which is electrical current, which is usually E, or rather I. And then Kelvin, which is temperature. This is absolute temperature, which is big T. Mole, which is amount of substance, which is big M. And of course here also we would usually add luminous intensity, which is candela, CD. Okay. So basically, why are these SI units important to us? They are representing base units, which we are using to measure anything and everything in this world. However, sometimes you will have something such as a different physical quantity, such as speed. Speed is usually V as a symbol, and its unit usually is meter over second. Now here you see that you're using meter, which is an SI unit of length, and S, which is an SI unit of time. Of course, we can also use kilometer per hour, which is something that we oftentimes use. However, meters per second would be derived SI unit. So this would be a derived SI unit. SI unit, whereas here these ones would be base. knowing these SI units also tells us that in physics, we are using metric system, not imperial system. So this is a very good start on this. One more thing that I want to kind of say while we are here as well is the topic of prefixes and of different types of amounts of things. So for example, oftentimes you will have a centimeter, which is 1/100 of a meter, 1/100th of a meter. Or if we want to write that in a different way, it would be 10 to the power minus 2. So 1 centimeter will be 10 to the power minus 2 meters. Okay? So for example, as well, we can have a kilometer, which is kilometer, which is what? Which is 1,000 times a meter. So 1 kilometer will be 1,000 meters. Here, usually, we have different types of prefixes. I will not go too much in detail. However, knowing them is important, especially going to convert from one to another. We will see some of them in the examples as well. Here, we are starting with physical quantities, which are length and time. And length and time are both base physical quantities, and then, for example, we will have volume, which will be derived. We will see how. So here, to measure length, usually we will always have an instrument. In physics, we always have instruments to measure something. So ruler, or a rule, as it is oftentimes referred to in Cambridge, is a device that helps us measure length. Now, the accuracy is related to how correctly we can measure this. So for example, here, if we want to measure it, this would be probably, if these are centimeters, be 5.1, 5.2, 5.3. Yeah, so the length of this 5.3 centimeters, this would be this length, right? Okay, now next thing that we would measure, which is closely related to length, is measurement of volume. To measure volume of different types of objects, usually we will be using again length, because usually, for example, for a cube, cube of sugar, if it all has the same size, which is a, and a, volume will be just a to the power of 3. Now, in this case, this is very easy because this would be a regular object. Q would be a regular object, or some type of cylinder, or any type of things that we can do measure geometrically. However, for irregular shapes, we are using measuring cylinder. Now, this measuring cylinder will usually be graded in milliliters. Milliliter and a centimeter cube is the same thing. It is a completely same thing. Liter is a measurement, a unit of volume, and centimeter cube as well. We are just expressing them in different ways. So, for example, oftentimes you need to describe how to measure an irregular object in with the help of measuring cylinder. Here, usually you will have certain amount of water that you will add inside of the first cylinder which you are beginning at, and you will measure the length here, avoiding the parallax error, which means you will be looking at the eye level of this measuring cylinder, and you will also have something called a meniscus, and you will be measuring from the lower part of that meniscus. So this is very, very important. So it has to be from this perspective here, not here, okay, not there. So this is something like a lowermost part here. It's called the meniscus, and you will measure it from that perspective, and you will say here, in this case, let's see, because I made it a bit complicated. Let's see, here it's going to be 20, so this is between 21 and 25, so it's going to be 24. here. It's going to be 24 as it is red here. And then again, after we submerge the irregular object, which is this one here, it will be 31. So how can I get the volume of a regular object? I will just subtract these two values, 31 minus 24, and I will get 7 centimeter cube or 7 milliliters. Oftentimes, for very, very small lengths, small thicknesses and so on, we will be using micrometer screw gauge. The accuracy is 0.01 millimeter. It is very, very small, and it has 2 places of reading it. There isn't much focus on this. This is something that is useful to know, but it is only important to know that we are using micrometer screw gauge for very small lengths. So, for example, for paper, if we want to measure paper, thickness of paper. Now, here also we have a trundle wheel. This is something that helps us measure length, which is not straight, for example, irregular length, different types of distances. We do not mention this much. A stopwatch can be analog and digital. It's an instrument that we use to measure time, of course. So we do not use a watch to measure time. We use a stopwatch, because stopwatch is something where we can control what is happening here. So for example, here this is hour. This part here will be related to the minute. Then we will have seconds. And then in the end, we will have milliseconds. We need to be careful here, because, for example, in this case, we have, if I'm asking how many seconds are there in this, like what am I reading here, you will first need to say that 1 minute is 60 seconds, and that will be plus to 23 seconds, right? And then plus to 0.47 seconds, because they are milliseconds, they are parts of seconds. So this will be in the end your result after you add all of these. We also talk about a pendulum. Pendulum looks like this. This is the one where it's oscillating. Most of the time, the way we will be measuring when we need to draw it, usually we will take a pendulum from this position and then put it in this position with our hand, and that pendulum will then swing all the way to the other side and then go and then come again to the side where it was where its oscillation started, right? Where its oscillation started. So basically, a way to measure this, it can be in different ways. However, it has to go through all of the positions. So it has to go completely to the left, completely to the right. So here you can see how that looks like. So basically, this was the first position, and then this was the second position, then it was third, and then it came back to the fourth position, and then a fifth position. This is also something that is very important. So to do a full oscillation, it needs to go both ways. So multiple readings are important for us because they are helping us with accuracy. Thickness of paper, for example, of 100 sheets. If we want to measure thickness of one paper, we will usually measure 100 sheets, thickness of 100 sheets, because this will lower our mistake, like error. Additionally, time period of a pendulum, for example, it is very, very hard for a naked eye to kind of react properly to just looking at a pendulum that goes left and right, and to determine where does it stop, where does it, like it's very hard for our eye, especially with very, very small pendulums where the swings are not very, oscillations are very small. So usually what we do, we take 10 of these periods, and then we divide the time that we get with 10. Okay, so this is as far as the length and time goes. We have talked about all of these aspects, and hopefully you know them as well. Now let's continue. Motion. Now motion, or rather this was a preparation for motion because it was physical quantities. We have a lot of learning objectives. All of these learning objectives are in one way or another concentrated in this slide only. So let's see first what the learning objectives are. So we need to understand that a scalar quantity has magnitude only, and a vector quantity has I just want to highlight this, and a vector quantity has a magnitude and direction. Up to this point, we didn't talk about scalar and vector quantities in this revision. So now we are reminding ourselves about that. So scalar has a magnitude only, or only value a number, whereas a vector quantity has a magnitude and a direction. And there are examples of these, of course. So for example, we need to know that distance, speed, time, mass, energy, and temperature are what? They are scalar values, quantities. And then we need to know also that force, weight, velocity, acceleration, and gravitational field strength are vector quantities. Okay, so these are vector, so we need to know this. This is a fact that we just need to memorize. We also need to be able to define speed as a distance traveled per unit time. So for example, when you have a question in which you need to define something, it doesn't mean that you are just using the equation. Of course, you need to be able to know this equation and to use this equation as well, which is very simple. V equals S over T. And as I am here, I will just draw us a very small triangle that we are usually using to calculate this and to remember it easily. So this will be V, this will be S and T, and this makes it easier for us to manipulate this equation. We need to define velocity. There is a difference between velocity and speed, as speed in a given direction. This is not completely correct because velocity is not distance over time in a direction, but displacement over time. And there's a difference between displacement and distance, and we talked about this. But for coordinated sciences, this is not very important because we're usually talking about speed and not velocity. Velocity and speed are not the same thing. And velocity is not always just a speed in a given direction. It is a bit more complex than this. We need to recall and use the equation, which is average speed, is total distance traveled over total time taken. Another way to write this is with the delta, which is that V is delta S over delta T. Point here is that the average speed, no matter how the speed has changed throughout a certain travel, in the end we are talking about the average speed. And this is something we are considering at this level in coordinated physics. Know that an object moving with increasing speed is accelerating, and one moving with decreasing speed is decelerating. So basically, again, you need to know the words. What is acceleration and what is deceleration? And in this context, you can have a negative and positive value as well here. So increasing speed is acceleration and decreasing speed is deceleration. You need to define acceleration as change in velocity per unit time. So this is basically, the definition is change in velocity per unit time, and the equation is A equals delta V over delta T. I'm gonna again put this in a simple format of a triangle, and usually this will be A, V, and T. Of course, we are talking about change in an average speed over average time, but for our purposes of coordinated sciences and physics, just knowing this formula in this format and being able to use it is sufficient. Now, of course, you need to know that deceleration is negative and acceleration is not an acceleration. Acceleration will be positive. So, and you need to use this in acceleration. So basically, it's a very important formula, same as the one above. I would also like to add a unit for both of these, because for speed the unit will be meter over second, an SI unit, although we can use kilometer per hour, and we need to be careful with this as well. And here we will have meter over what? Second square. This is something that a lot of the time we can kind of mix up, I notice. Okay, so sketch, plot, and interpret distance time and speed time graphs. This is very important. This is important also for paper 4 and paper 6, for all of them, understanding these graphs. So if you have issues with this, I would advise additional revision of this topic, because it's very important, and the concept of a gradient will repeat throughout the whole physics. Determine qualitatively, so not quantitatively, from the shape of the graph when an object is at rest, moving, and at a constant speed. So you need to know this. We will see accelerating and decelerating. So oftentimes, if you know how to interpret a graph, you'll know how to say how an object is moving based on that graph. Calculate speed from the gradient of a straight line section of a distance time, and calculate distance traveled from the area speed time for constant speed or constant acceleration. Here, we will also mention that in a bit, but speed from a gradient of a straight line of a distance time graph, let's just remember that a general formula for a gradient, I think I wrote, okay, it is gradient or slope, it's the same thing. It is rise over run. Okay, rise over run, and that rise over run usually looks like this. This is the line, and then rise goes up, right? So this will be rise, and then this will be run. So this value of rise divided by the value of run. And then we need to calculate the distance traveled from the area under a speed time graph. This will mean the following. Area under a graph, it is also very easy to calculate. So if I have a graph and a straight line as a linear, then for me to calculate the area below a line, which I need to color in somehow, because I want to know this is area. So, and I say that this is some value A and this is some value B, because we see this is a triangle, straight triangle. It would be A times B divided by 2. Okay, so this would be area under a graph. Of course, you need to be careful. It can be something different. It can be different, but this is one. It can be straight and so on. It can be a straight line. It can be something resembling not a triangle. So you need to be careful with this. Determine from data or graph shape when an object is moving with constant acceleration. Yep. From constant acceleration or changing acceleration. Okay. When we have a constant acceleration and changing acceleration, they look different in a speed time graph compared to a distance time graph. So constant acceleration, I'm gonna just draw it here. So this is, let's imagine this is a speed, rather I'm gonna speed time, okay, and speed time graphs. So for constant acceleration and speed time graph, it will look like a straight line going up, yeah, and changing acceleration will be some type of curve like this. Like it will not have a straight line. It will be changing acceleration in a speed time graph. Okay, so calculate acceleration from the gradient of a speed time graph. Same thing. Here we have a rise over run. We will just be using speed time instead of distance time. So calculated on the graph. This is, I would say, maybe one of the hardest part to understand. A lot of information, I would say, relatively but also a lot of the questions are coming from this area as well. So I would suggest really revising this well. So let's see. Speed is distance moved over time taken, and we know that the speed is a scalar. Let me see if I have a... No, it doesn't matter. Okay. Yes. So, and this is the formula that I've just wrote you previously. Here we have a velocity, which is magnitude with the direction, somewhat, we can say, because you see here there are two cars. One is going to the right, or east, to the right or to the east, or this one is going to the left. To is to the somewhere left is not sufficient. It has to be to the left. So yes, it's a velocity because it's a vector, because it has a direction, where we have for speed we only have a magnitude. Acceleration, let's see here. We're gonna go back in a second to see here what is happening with something that has this type of distance over time. So if we had a distance over time which was a straight line like this would mean that there's no acceleration that we have. So no acceleration, but distance. Okay, this is a constant speed, constant speed. And this is not a constant speed. This is speed that is changing. And if speed is changing, that means that I have acceleration. So this is acceleration. And we know that constant speed cannot result in acceleration. Only changing speed results in some type of acceleration or deceleration. And this is the formula that we've just set. So to calculate rise over run, we will have to go and draw a triangle here and say, okay, this is the rise here is 1.3 over 0.5 and so on and so forth. And let me see if, yes, that's basically it. When you are drawing a graph, never forget that you need to write a label as well as a unit. Of course, you don't write a unit, then that does result in getting points if a graph is important. Acceleration is change of velocity over time. Here we have u, which is starting velocity or starting speed. Usually in our calculations we don't really see that much. We usually just begin with v over t. Acceleration and deceleration we of course have here. Here is a velocity over time graph. Here again, if we would want to make this a proper graph, we would have to add meter over second. Okay, this is one way. Another way is to put it in parentheses, which is second. So this is something that usually we would want to do, but here this is just a graph, velocity time graph, that is just showing us something. Here we have a in this area here, we have acceleration. We actually don't have acceleration because it's a straight line. Well, constant line, not straight line. All of them are straight lines. So in this area, first part here, I will have constant velocity, which is zero. Zero or constant velocity is the same thing. This is why this area as well as area number 3 are both just flat lines. So we have 4 areas here. First area will be constant acceleration. Well, actually, first area will be constant velocity, which is 0. Then constant acceleration, and then constant velocity, and then constant deceleration. And if I would ask you, is acceleration as a value higher, like is a car or anything that might be moving in this way, is it accelerating fast? Like, is its acceleration higher than its deceleration? What would you say? Knowing some information that you know about the steepness of the slope. So apparently here we see that number 4, like this area here, this slope is more steep than this one here. This means that an object that is moving and is represented by this graph is decelerating faster than it is accelerating. So the higher the slope, if this is so this slope, and let's say slope this one, if I would ask which one of these slopes is representing higher acceleration, although both of them are constant, then you would say it is the one with the red because the slope is steeper. Free fall is a type of motion which is a very good example of a different type of acceleration, deceleration, and forces and so on. And to understand really the free fall, you also need to understand the forces as well. But here in this one, we have this air resistance, so the only force acting here is weight. We also talked in our classes, we talked about terminal velocity and stuff like this, in which after a certain point air resistance and weight kind of even out, and then the body is from that point on just falling in a constant speed. But in this case, we are just talking about downward motion and basically just being constantly accelerated with acceleration of 10 meters over second square. This is A or G. G is something small g is something that we talk about a lot. It has two things that it represents. It is approximately 10 meters over second square, or sometimes it is 981 meters over second square. Knowing this constant is important. This is the acceleration of the Earth, and also it is strength of the field, Earth's field, gravitational field, strength of it. So yeah, it looks like this because the acceleration will continue on happening. Let's see. Okay, let's continue now on the mass and weight. Now, since we already talked about mass acceleration here, this is kind of our first introduction to force without going to forces yet. So mass and weight are a lot of the time kind of confused with one another. Let's see in the learning objectives what do we need to know so we know what to focus on. State that the mass is a measure of the quantity of matter in an object. So mass is basically intrinsic value. Okay, it's an intrinsic value. So whether you are on a moon or on Mars or on Earth, it doesn't really matter. You will always have the same mass, and we know that the unit of mass is kilogram. However, the weight, this is very important, disambiguation between two of these things. Weight is the gravitational force acting on an object with mass. So this is basically, weight is the effect of the gravitational force acting on an object with a certain mass. So even though you have 60 kilos, let's say, on Earth, you will have actually the same kilos on the moon as well. But if you were standing on a weighing scale, you would see a very different effect. You would probably see an effect that where you would have significantly less weight, but not less mass. But in our everyday language, weight and mass have almost the same meaning, but it is important for you to understand this difference in physics context. We need to define gravitational field strength as gravitational force per unit mass. So this is the thing that we just talked about before, and I'm gonna write, this is one of the formulas that is really relevant, and I would also like to put in a triangle way so that it's easier for you to kind of focus on it. So this will be W, which is weight, and this will be M and G. So this is basically relationship between mass and weight. The way we also, as I said, we talked about this gravitational field strength, which we also know is same as the acceleration of the Earth, and its unit is sometimes Newton over kilogram if we define it through weight, and sometimes it is meter over second square if we define it through force, through what we talked about before, through acceleration. Now, weight is in newtons. I'm gonna just write these units here. And Newton is a SI derived unit. Gravitational field strength will be in meters over second square. And mass, of course, in this case will be in kilograms, and kilograms are also SI unit. They are not grams. This is an interesting tidbit. And one of the things which are interesting in physics, there is a whole story why it is this way, but we're not going to focus on that now. We need to describe weight as the effect of gravitational field on a mass. So weight, this is the difference between weight and mass. Mass is same everywhere. It is a measure of, it's a basically characteristic of an object, let's say. Whereas weight is the effect of gravitational field on a mass. We know that gravitational field strength is equivalent to the acceleration of free fall. Acceleration of free fall and gravitational field strength, same thing. Approximately 9.8 newtons over kilogram. Now, near Earth's surface. Of course, this will change slightly depending on where on the Earth you may be and so on, but that's not something that is relevant for us. Earth's surface is important here. Define now again. Let's return to density after we just go through mass and weight. So here, for example, you will have a, let's see. So mass is amount of matter in an object, which is in a kilogram, a property that resists motion, which is also inertia, but we don't talk about inertia in this context. This is a property that resists motion is inertia, not mass. Inertia and mass are very much related to one another, not the same thing. But yes, this is, in this context of the coordinated physics, not a relevant thing. Weight, force of gravity on mass, force of gravity, because gravity is also, it's also a type of force. This is why it has a unit of a Newton, which we see here. So for example, here we have a solar system, Sun, Jupiter, Saturn, and so on, and you see how all of them have vastly different forces of gravity, basically. So, and this is of course related to their size. So the bigger they are, the more gravitational force they have, because it's related to mass. So interesting thing here is to say that even though gravitation is not visible maybe between two objects which have very, very small mass, for example, between two people, or even, for example, between two trees or something very, very big, two elephants, I don't know. It technically exists. However, it's so negligible, it's so small that we cannot see the effects of it really much. This is why we need to know that gravity is a force which is always attractive, happens between any two objects which have mass, any mass, non-zero mass. And in the case of Earth, which is to us almost infinitely bigger, although it's not, of course, infinitely bigger, the reason why Moon is rotating around the Earth and not vice versa is because Earth has higher gravity, and the reason why we're going around the Sun and not Sun around us. Here we also have, I do not know what I've deleted here, but this is a scale. So this is something that measures mass, but also something that measures weight in a way. So this is a scale. We would say weighing scale, but it is a scale that is measuring kilograms, let's say. And here we would have something called a dynamometer or Newton meter. Dynamometer. Dynamo, because dynamics is a science of forces in physics, or Newton meter. And here, for example, we say that it is measuring in newtons, but it works in the same way as a scale does, really. Just it has a spring here, where a scale has a weighing scale goes like on both sides, and we kind of are looking here what is happening with our measured mass. And also we have a different types of scale as well, which inside of itself again has a spring, and we will learn about springs as well when the time comes. Now, what is density? Density is, again, a physical quantity that is derived, and it has a very interesting, I would say, new symbol that you didn't see before, which is says, which we pronounce as rho. So it's a Greek letter. So here we will have a triangle again. And again, MV. One of my students also told me that density is a broken heart equation. Very dramatic, but very, very nice to remember. So M over me, mass over volume. And I'm gonna add again units. Mass will be of course kilograms. V, which will be meter cube. And for rho, we will have what? Kilogram over meter cube. Sometimes you will also have grams over centimeter cube. Of course, because we can use different sizes of things. So here, as I've said, we talked about, let me just go into highlighting. Yes, so define density as mass per unit volume. Recall and use the equation. Describe, don't write it as P is my only thing. Like it is rho, it's a different thing. Describe how to determine the density of a liquid, a regularly shaped solid, and an irregularly shaped solid. So this is basically, the whole point here is to understand how to measure volume. This is the hard part. The second part, like there are two things here that you need to know. One is how to determine a volume of a regularly shaped and irregularly shaped solid, which is basically something you already know from before, and this displacement thing, which is the one that I've described you above with the measuring cylinder. And then the second thing here is when you actually do get your volume correctly, then you need to plug it in correctly into the calculation. This is what makes calculation of density tricky. Not really that it is that hard, I would say. Determine whether an object floats or sinks based on density data. This is very nice because if whether something will flow or sink is also related to the shape it is in, but we don't talk about that. We just talk about like two identical shapes and their different densities. And for example, if we have wood and if we have, iron, we will of course have different type of effect because wood will be less dense than water. Or for example, if you have some things like that are floating in air, like helium, for example, which has lower density than air. Okay, so let's continue here with density. This is the equation. You see here they chose grams over centimeter cube because this is more realistic. This is something we do see every day. Why? Because centimeter cube, let's not remember, is related to milliliters, and measuring cylinders usually measure in milliliters, right? 1 milliliter, see? And gram, of course, is more realistic than a kilogram because kilogram is a quite hefty mass when we're measuring very small things. This is Eureka can. So usually we will have a measuring cylinder, and in this measuring cylinder, which is usually graded in, as I said, milliliters, we will pour in some water. And then for the irregular shape, we will submerge completely, even though it might, if we want to calculate the density of that object, we need to have its mass and we need to have its volume, and then it's very easy for us. This is digital caliper. This is something also used to measure volume, well, to measure length really, and then to calculate volume for regular shapes. Here it measures precisely very small lengths. However, micrometer is more precise for very, very small things. Usually this one is digital, which is great. You don't have to read anything on 2 scales. Usually we don't use it much, but it's a good thing that we know. Floating is related to the density of the object and the density of the medium in which an object is. So for example, here you have a polystyrene block, wood and iron, and all of them have different density compared to water. In the first one, it is completely floating. It cannot be at all submerged. Second one, it is submerged somewhat. And you see also if you compare for example, for wood is interesting because it's partly submerged. And since it's partly submerged, it has density which is less than the density of water. And maybe you would expect it completely to float, but it's not that far away. Whereas density of polystyrene is way below of the one of water, so that's why it's completely above. Whereas the iron block should be completely on the ground, is completely submerged. An interesting thing here that you need to know is, I'm gonna write it like this. If you are measuring, this is very bad, I'm gonna delete this. This is what I want to write. So submerge completely. So for volume measurement. Okay. So if we wanted to, if this was an irregular object, I would not be able to measure the density of it, even if I had the mass, if I couldn't completely submerge it. That's why I need to see the displacement of water. This is not sufficient. It needs to be completely inside. So yes, forces. This is a general overview of forces. What we want to do here is, let's see what we have first. Let's go over the learning objectives very quickly. We want to determine the resultant of two or more forces acting along the same straight line. Resultant of forces. I'm gonna just make this a bit smaller. Know that an object either remains at rest or continues in a straight line at a constant speed unless acted upon a resultant force. This is Newton's first law. This is Newton's first law or law of inertia. We will recall and use the equation F equals ma. This is also very similar to the version. This is Newton's second law, and also a version of a connection between weight and mass is a version of this law. And know that a resultant force and acceleration are in the same direction. Let me just again draw a very quick triangle formula for this as well, because it's important for us to remember. It will look like this. FMA. And this is the formula for force that you're going to be seeing the most, like the most often of. Okay, next, describe friction. Describe friction as a force between two surfaces that may impede relative motion and produce heating. Includes air resistance and drag. So we have air resistance and drag as the types of friction, and this is a force between two surfaces. Know that forces may produce changes in size, shape, and motion of an object. This is how we also define our force when we talk about it. Know that force may produce, sketch, plot, and interpret load extension graph for an elastic solid. Very quickly, it looks like this. Usually, the one we talk about is that we have a force here, or a load, and extension, which is delta x. And delta means it's an extension and not the whole length for an elastic solid. And lastly, define the spring constant as a force per unit extension, which is, this is equation, and it's called Hooke's law. Hooke's law. And define and identify the term of limit of proportionality on a load extension graph. Quickly, it looks like this. If this is a, okay, so this will represent a slope here, will represent of this part will be k, which is f over delta x. And at this point here, we will have something called a limit of proportionality. Now we're going to see this also. This is something, just an overall overview of the things that we need to know here. So first, effects of forces. Forces can change size, shape of a body, and motion. Extension load graph here we have is related to springs, and here we have two springs. First one is the one which is not extended, and the second one is the one where we have extension, and this extension is delta x, because this is some value of x1 and this is some value here, and then here is going to be x2, and when we subtract these two values we get delta x. So extension is the final length minus the original length, in this point 1.4 centimeters. I like to say, mark it as delta x, because this way we kind of know that it's a difference between two values. And this is a load, which is another also term that refers to weight. How is that represented? Here we have force and extension, and it would usually be like F here, which is extension, and then in parentheses or with a slash we will have Newton here, and extension will be delta x, and in here we will have a meter. And here we will have a limit proportionality, and we see, for example, that until a limit of proportionality, the line here is straight, and the straight line means that in that area Hooke's law is obeyed. So if I can make a note here, I would say that in this area, okay, until while it's straight, so Hooke's law is obeyed. And here, after this point onwards, Hooke's law is not obeyed. Doesn't work anymore. Okay, after the limit of proportionality. Hooke's law says a material obeys Hooke's law if beneath its elastic limit the extension is proportional to the load. So for a graph of load and extension that has a straight line, okay, that has a straight line. If it has a curved line, it means that there is no obeying of the Hooke's law after that point, okay? Spring constant is F equals kx. Extension is x. I like to say that it is delta. Unit of K will be F over X, which will be Newton over meter, usually. It can be millimeter, it can be also meter, whichever. So I would also like to add here a triangle that I forgot previously, which is another triangle, F K delta x. Resultant force. What is a resultant force? We didn't talk about scalars and vectors too much, but here in resultant force and talking about force overall, we remember that a force is a vector. It's a vector value. It's a vector quantity. And here, for example, we have a resultant force. In this case it's 0 newtons, because we have 5 newtons on one side and 5 newtons on the other side, so this would be 5 newtons minus 5 newtons mathematically, but usually we kind of determine this from looking at it, so be aware of the direction of the forces. And in this case, for example, we have 3 newtons and 7 newtons both to the right or to the east, and therefore the resultant force will be addition of these two values. Here we have 7 newtons to the one side and 3 newtons to the other side, and then we will have 4 newtons, but the resultant force, because 7 newtons, when we subtract 3 from it, I will have a resultant force that will look like this, and it will be 4 newtons where to the left, okay. This is the second Newton law, and this is the format of it, and you see it's actually a type WMG. This is weight, so weight is a type of force, mass is already mass, and acceleration of the gravitational field is a type of acceleration. Now here, we also have different types of forces. We have tension. Here in this way, you see weight has a direction downwards because gravitational force is always attractive force, and tension is opposite because tension is always, it's an elastic force. Air resistance, of course, acts upwards, whereas weight acts downwards. So the masses remain at rest, the parachute travels at a constant speed. So if I have constant speed, or I have rest, which is speed is equal 0, or speed is equal constant, that means I do not have a resultant force. This means that I do not have a resultant force. A body remains at rest or continues at constant speed in a straight line. Friction is a force that opposes the motion of an object. Energy loss, for example, kinetic energy is transfers to heat. Air resistance, or for example, drag. Surface texture can affect the friction. Direction of motion, whatever the direction of motion is, and therefore the force that might be towards that direction, the friction will always be opposite, and weight is going to be on an angle like this if it's angled moment. Now, turning effect, we don't have much. This is the last part of this part. However, although not very hard, sometimes it can be a bit tricky for students. Turning effect, another word for turning effect is also torque, and also moment of force, because moment of force is also effect of force in a way. Understand what it's meant by center of gravity and know its position for regularly shaped objects such as rectangles, spheres, and cylinders. Describe an experiment to determine the position of center of gravity on an irregular shaped. So center of gravity of an irregular shaped plane lamina. So this is basically, if I need to draw something, here you're gonna have a rectangle, let's say. This is going to be a regular object, whereas some irregular object might be like this. Plane, because it's laminate, we consider it 2D. It's not 2D, but for example, very, very thin paper that we cut in a certain stiff but thin paper that we cut in a way that we can determine the center of gravity. Describe qualitatively the effect of the position of the center of gravity on the stability of simple object. Basically, this means the lower the center of gravity, the more stable the object. And also it means that on the place where the center of gravity is on a body, you can also balance that object there. The moment of force as a measure of its turning effect, and give examples. Opening up doors, for example, is the best example, or windows, or car doors. Define the moment of force as moment equals force times perpendicular distance from the pivot. We have a formula for this that we also can write in a triangle, and it's going to look like this. M, force, and D with a little opposite T, which is basically perpendicular, right? Like a perpendicular, which is a right angle. You need to know this equation, of course. State that when there is no resultant moment, an object is in equilibrium. No resultant force and no resultant moment. This is equilibrium. Equilibrium is two things, really. Apply the principle of moments to situations which with one force on each side of the pivot balancing beam. Also, how I taught you, the principle of moments basically says the sum. The symbol of a sum is this. Sum of clockwise moments equals to a sum of anti-clockwise moments. This is principle of moments, POM. Maybe it's an easier way for you to remember. And you must never forget this. usually you do have a question from here. Describe how pressure varies with force and in area everyday examples. Define pressure as force per unit area and use this equation, which is force over area. And again, I will use a triangle, pressure, force, area. Unit of pressure will be Pascal. Okay. So let's continue now to the last part of the motion part. So turning effect, moment turning effect of a force. So basically effect of a force that is acting on a certain distance from a pivot is, in other words. It causes objects to rotate around a pivot, pushing open a door, for example, using a crowbar to open something and stuff like this. And for example, if you have a door, I'm going to probably now draw it very, very bad. But let's say if these are the doors that are open, right? And you have a handle here. I'm going to now just delete this part so it looks like I'm actually drawing something. And depending on where you are acting with your force, you can act at this point or you can act at this point. You will have a different moment of force because the hinge is here, the pivot is here. So the farther you go away from this, which is your D, perpendicular, the bigger effect you will have. The bigger effect you will have. So let's see. This is the formula that I've set. Moment, Newton meter, force, and this is distance from a pivot. In this example, we have actually an example of use of principle of moment of force. So what you need to look at here is, okay, you have a pivot, okay, but you should not be confused. Sometimes you can, as here, for example, you see you have force F2 and force F3, and they are all on the same side of the pivot, like on the right side of the pivot, but they have a different effect. So you see, for example, the one F3, let's begin with it, it will try to push up, and it will have a counterclockwise effect. This one will try to push down, and it will have clockwise effect. I mean, effect will be in a way, if it pushes, if it's the most strongest one in the system, what will the effect be? And F1, how will it act? Like this. So you see that basically F1 and F3 are compatible. They both want to kind of tilt the whole system to the left. Okay, so this is why we have F1 times D1, because we are always looking at the distance from the pivot, and F3 times D3 on the same side. This could have been also on the left. It doesn't really matter. The equation is symmetrical. And here only, so basically the sum of counterclockwise moments equals to the sum of clockwise moments. So clockwise moments here is only F2, like F2 times D2. And of course, this has to be an equation which you then solve. So force provided by shelf. So this is a very typical problem as well. Designing a shelf that doesn't collapse. So you basically need to see how it will work. This is the pivot, and the weight of the vase is trying to push it down, while force provided by a shelf is trying to keep it up. So you have different distances. So it's going to be force provided by a shelf times 30 equals the weight of a vase times 50. Equilibrium. An object keeps doing what it's doing. So it's in a balance, equilibrium or balance. So if it's moving, it will continue in a straight line. If it's stationary or non-moving, it's going to continue like this. It will not stop turning. Conditions: no resultant force and no turning effect. Very important. This is the principle that I was talking about. But also no resultant force. So resultant force will be 0. Resultant force R will be 0. Let's see, next thing is center of mass. Center of mass, center of gravity. There is a whole story here because there is a difference between a center of mass and center of gravity. But here we're talking about center of gravity. Most of the time they are the same thing. The only difference usually is when you have a very, very tall building, which the taller it is, it will have a different effect of gravity, although its mass might be different, or distribution. So for us, center of gravity or center of mass is almost the same thing. in the context of physics you are learning at this level. The point through which the weight of an object acts, located at a point of symmetry. So these are all regular objects. So basically, if you put two lines, symmetrical lines, and divide an object in two symmetrical parts, you will basically have at the cross section of these two lines, you will have a center of mass or center of gravity. That is center of gravity, not or. However, how to understand and how to figure out the center of mass or center of gravity of a irregular object, This is the so-called lamina, which is basically a very thin, stiff cardboard, let's say, or paper that is cut in uneven way. So the center of mass, you put it on something, you hang it on something, and then when you hang it, you also put like something called like a plumb line. You remember, it's like a little line that it hangs here. Usually you will have like a thing here, and it will go somehow like this. Yeah, it will have those things, and it will be hung there, and it will orient itself so it can hang down. So you will hang it on few different places where you can, and each time it will separate itself, like the line that goes through it, it will be put through the middle. So basically in the intersection of the two lines, we just need two, it will be the center of the mass of this irregular subject. Usually you are asked to describe this. Stability, most stable. What's the relationship between stability and center of mass or gravity? Wider base means it is more stable. Lower, because wider base also means lower center of mass. Distribution of weight is also important here. This also means, a real life example, for example, is a difference between, let's say, Ferrari car and a bus. Ferrari car, which is very flat, and its center of mass or gravity will be closer to the ground compared to a very tall bus like a double-decker, will be more stable. It will be way harder to turn over a Ferrari than it would be, for example, a bus. And the last point here is pressure, concentration of a force. Concentration because it means it's related to the area. So pressure is force over area. It has a special unit which is Pascal, but this Pascal is really Newton over meter square. And if you get something like a kilonewton or any type of centimeter square or something, know that you cannot say that is Pascal unless you convert those units. So drawing pin and a thumb tank. Here we also have an example in book as well, which is related to the difference if someone was stepping on you in a high heel or, for example, an elephant. Which one would you prefer? Of course, you would not prefer an elephant, but the point is the bigger the area, if the force is the same, or the bigger the area through which the force is acting, the pressure will be lower. So that's it for this part, first part of the motion part. Motion part is one of the trickiest part, I would say, to kind of revise, and you have a lot of questions from this. However, there will be other parts as well that we're going to be revising in different videos. So good luck with that, and thank you for watching.